Welcome to the module, Basic Bend Technology. Topics in this module include bending process, bending types, machine concepts, tools, bend guard, and ACB, automatic control bending. Learning time approximately 1 hour. Welcome to the first module of the Trumpf bend-inch training tutorial. To properly program for your operators, knowing the basic operation of the true bend press brake will be essential. In this module, you'll acquire the basic concepts of press brake operation. After completing this lesson, you should be able to identify features of air bending and bottom bending. Identify the parameters of the bending process. Let's begin with an overview of basic bend technology. True bend press brakes are designed to bend flat sheet metal into three-dimensional objects. Bending takes place once the punch tip makes contact with the material and continues to press it into the die. Generally, when bending material, 5 parameters are used to overcome the compressive and tensile strengths needed to create a bend. Changing any one of the 5 parameters will affect the positioning of the beam or y-axis. The following parameters determine the traveled distance of the y-axis. Programmed angle. Material type. Material thickness. V. Die opening. Length of bend. Please select the launch button to watch a video that demonstrates the effect the 5 parameters used to create a program have on the y-axis position. Once finished with the video, please click on the to demonstrate the effects the 5 parameters have on the y-axis. We will use the Task 6000 controller for emphasis of these parameters. Here are the 5 parameters for the current program. Please follow the yellow circle. The Y-rec is the positioning of the y-axis based on the 5 parameters in the program. Note the 6.87003 Y-rec value at Let's change the angle to 90 degrees. Notice the changed Y-rec. It has decreased due to the increased program angle. We will do one more parameter. Let's change the material type to stainless. 1.4301. Again, note the change in Y-rec. It has decreased from 6.59271 to 6.58983. It's important to note that both the programmer and operator ensure that the correct parameters are used for part creation. In later portions of the training, you'll learn how to use the programming applications to plan different types of bends throughout the bending process. First, you need to understand that there are 2 basic types of bending: air bending and bottom bending. Click the markers for more information. Here is a side-by-side comparison of air bending versus bottom bending. Let's pause here and review the bending process and bending methods, air and bottom. Please select the 5 parameters that affect the travel depth of the y-axis. That's right. The bend length, material type, V die opening, bending angle, and material thickness all determine the y-axis position for air bending. Which type of bending uses the highest tonnage, pressure? Sorry, that's not correct. Bottom. In which type of bending does the programmer program the depth of travel for the upper beam? Sorry, that's not correct. With it, you have now completed the first section of Module 1, Bend Technology, Welcome to the section, Bending Concepts. Understanding how sheet metal parts are produced is an essential part of the programming process. When bending material, the metal becomes deformed and stretched. The stretching that occurs adds to the overall length of the formed part, a process called bend allowance. In this section, you will acquire the basic concepts of bend allowance and bend deduction, and how these processes affect part creation. After completing this lesson, you should be able to identify bend allowance, and, given product specifications and a bend deduction chart, identify the correct bend deduction. The term bend allowance refers to the amount of stretching that takes place when the material is formed around the tip of the punch. The stretching factor that's involved needs to be noted when programming in order to achieve the correct blank size. Here's a diagram to help explain bend allowance. When a material is formed around the punch tip, the material bends into a particular shape by stretching. When bending, the compression and tensile stresses of the material have to be exceeded. Because the material has a natural tendency to regain its original shape, spring back, the material has to be overbent to overcome those stresses in order to get the programmed angle. Incidentally, the area between tension and compression is called the neutral axis because it goes through neither tension nor compression. This is what causes spring back. The neutral axis is approximately half to two-thirds the width of the material thickness. Because the material tenses and compresses, it has a tendency to return to its original shape after the pressure from the upper beam has been removed, during what is called the decompression cycle. This tendency is referred to as springback. Different types of metal will react with different amounts of springback. To get the proper bend, springback must be taken into account when determining the bend angle. Let's return to the bend allowance. Charts like the one shown here are used to determine the bend allowance. For example, assume these are the specifications for a part. Go to the next page to read the procedure on how to determine the bend allowance. Here's the procedure for determining bend allowance. Take a moment to examine the bend allowance charts for other sheet thicknesses. Please click on the individual sheet thickness buttons to see the actual chart. When finished viewing the open bend allowance chart, click on the X in the top right corner to return to this page, then click the next arrow to continue. To demonstrate, welcome to the term. Take a moment to examine the bend allowance charts for other sheet thicknesses. Please in order to produce a part with the desired finished dimensions, something called the bend deduction also needs to be taken into account. The bend deduction is the amount the workpiece will stretch when bent as measured from the outside edges of the bend. As shown in this formula, the bend deduction is equal to 1/2 of the bend allowance. The bend deduction H has to be subtracted from the flange length in order to position the back gauge properly. Otherwise, the workpiece will not stretch to the proper length. When metal bends, what force causes the metal to stretch along its outside dimension? Yes, that's right. The bending process causes the outer. Assume these specifications for a part. According to the chart, what is the bend allowance in millimeters? Sorry, that's not correct. According to the chart, when using an 8 mm V, let's work from the previous question. If the bend allowance is 2.36 mm, what is the bend deduction? Correct. The bend deduction. You have now completed the second section. Welcome to the section on press brake safety. Now that you understand a bit about how Trumpf press brakes work, let's talk about some safety features you always need to have in mind when programming for this type of machine. In this section, we will discuss the safety features found on the press brake that you will program to keep the operator safe. After completing this lesson, you should be able to identify the operating principles of bend guard, identify different bend guard modes, and assign the correct bend guard mode for a program. The first safety feature discussed will be the mute point. The mute point is an OSHA/ANSI regulation. It is the maximum required setting for the height of the punch tip above the workpiece when changeover from fast approach speed to pressing speed takes place. Note: the mute point should always be set at 6 mm, 0.250, or less. Another safety feature of the press brake is bend guard. Bend guard is standard equipment installed on Trumpf press brakes. It is an optoelectronic sensor protection device that protects the operator, while allowing maximum speed during production. A laser transmitter on the left side and a receiver on the side create a 30 mm square beam that continually monitors the area below, in front, to the rear and to the sides of the punch tip. The beam moves at a maximum speed, up to 220 mm per second, between the upper travel limit of the beam, its upper dead point, and the point where the beam slows down prior to contacting the material. This slowdown point is referred to as the mute point. If the laser beam gets interrupted by an obstacle such as the operator's hand or the workpiece, the downward motion of the ram is stopped. Bending can be resumed by pressing the right foot pedal on the operator pedestal after the obstacle has been removed. This protects the operator's hand and fingers from being in the point of operation. Here's a video showing bend guard in action. Select the launch button to the right to watch a demonstration of bend guard on the press brake. 1. Note: the task 6 to dem. Is finished. In the bend application of the Trumpf, when the up with the video, click on the red X in the top right corner to return to this page. When the upper beam first begins its downward motion, it travels at a rapid speed, fast approach, until it encounters an obstacle or it reaches the mute point. As the ram continues to move downward at rapid speed, a line-by-line deactivation of the block laser takes place. Monitoring of the space between the punch tip and the material is continuously occurring. When the upper beam reaches the mute point, it will either change speed or stop depending on the bend guard setting chosen by the operator. The mute point is the pre-programmed height of the punch tip above the workpiece where the movement of the upper beam will change. The OSHA-regulated mute point is 6 mm, 1/4, however, on the true bend machines it is possible to set a mute point as low as 2 mm. When the upper beam is allowed to continue below the mute point, it switches to the working speed. At this point bend guard is no longer active. In the bend application of the Trumpf software, within the bending process menu, 1. You will select the process bending function. 2. The bending process technology data dialog box opens, and upon selecting the additional axis tab, 3. You will be able to select the desired bend guard mode. This information will be covered in detail later in the training tutorial. Note: by default normal is selected, however, your operator has the ability to modify the settings at the machine. There are 6 modes of bend guard. You will need to know which to choose based on the part to be created. Modes 1 and 3 are used to bend open profiles. Modes 2 and 4 are used to bend parts with side flanges such as a box. Modes 5 and 6, if selected, deactivates bend guard and cause the ram to move in a slow pressing speed throughout the entire bending process. Please take a moment and click one each number to examine the different bend guard modes available. Let's pause once again for a review. What bend guard modes stop at the mute point? Sorry, that's not correct. The bend guard modes that stop at the mute point are bend guard modes 3, 4, and 6. What bend guard modes can be used when bending open profile parts? That's right. Bend guard modes 2 and 4 are suitable for parts with side flanges, such as boxes. Bend guard modes 1 and 3 are suitable for parts with open profiles. Given a description of a specific bend guard mode, please select the correct associated icon. Rapid down movement of the ram where it stops at the mute point. To continue bending, step on the right foot pedal and the ram will continue travel at pressing speed. Sorry, that is incorrect. Bend guard mode 3 is the correct answer. It has a rapid down movement and stops at the mute point. At which time, the operator steps on the foot pedal again to change to a pressing speed of 10 mm per second. Given a description of a specific bend guard mode, please select the correct associated icon. Rapid down movement to where the ram is interrupted by the part and stops. Press the foot pedal again to move the ram to the mute point where it will stop again. To continue movement, step on the right foot pedal and the ram continues at pressing speed. Sorry, that is incorrect. Bend guard mode 4 is the correct answer. Bend guard mode 4 is suitable for parts with side flanges. Given a description of a specific bend guard mode, please select the correct associated icon. Rapid down movement of the ram to the mute point, it doesn't come to a complete stop, the ram speed then transitions to pressing speed. Sorry, that is not correct. Bend guard mode 1 will allow the operator to have continuous movement into the bend of the material. You have now completed the third section of Module 1, Bend Technology, Safety. Welcome to the Machine Axis section of the Basic Bend Technology module. At this point, you should be familiar with the different bend guard modes. We now want to focus on the axis of the press brake. An axis is the reference point for a range of measurement and direction of travel. The values input on an axis will control the travel path of that axis to establish its position to perform a particular bend. In this module, we'll discuss the different axes on the Trumpf press brake and how they affect part creation. After completing this lesson, you should be able to identify Trumpf machine axes and identify each axis reference or measured position. Y-axis, stroke and inclination of the press beam, upper beam. I-axis, lower die alignment, forward and backward. V-axis, crowning, deflection value. X-axis, forward and backward motion of the back gauge. R-axis, height adjustment of back gauge. Z-axis, left and right back gauge adjustment. Note, each axis is identified assuming one is facing the front of the press brake machine. The Y-axis controls the up and down movement of the upper beam. Y1 and Y2 are independent and can be adjusted for parallelism up to 10 mm on 5000 and 3000 series machines, and 1 mm for 7000 series machines. The crowning axis corrects deflections when bending long pieces of material. The V-axis is only important when bending takes up much of the die bed area. For shorter work pieces, the V-axis has little to no impact, usually under 200 feet. To achieve the most accurate crowning, the 5 parameters listed below must be accurate. 1. Material type. 2. Programmed angle. 3. Material thickness. 4. V-die opening. And 5. Length of bend. The I-axis is the front and back movement of the die bed via pneumatically controlled cylinder, standard, or optional CNC control. For the pneumatic I-axis, spacer blocks corresponding to the width of the die are used to adjust for distance in shifting. Attaching a flattening die to a flattening punch, the part will first be bent to an acute angle, then using the I-axis, the die is shifted and the part repositioned on the die for flattening. Please select the axis to receive information on the back gauge system. The X-axis is the front-to-back movement of the back gauge which determines the flange length of the bend. Values for the X-axis should always be entered as positive numbers. When negative values are entered, as in a bumping program, incremental movement occurs from the last positive value. The X-axis 0 reference point is the center of the die in relation to the front of the back gauge. Note, The closest the back gauge can get to the center of the V die is 3 mm, 0.118. The R-axis is the height of the stop fingers in relation to the top of the lower die. The R-axis can be positive, above the top edge of the die, or negative, below the top edge of the die. When you enter a value of 0 for a bend, the lower side of the stop finger will rest at the top edge of the die. The Z-axis is the horizontal movement, left to right, of the stop fingers. The Z-axis stop fingers are measured from the outside edges of the fingers in relation to the numbered rail on the RAM. What is the reference position or reference point of the X-axis? Great, that is correct. The reference position for the X-axis is from the center of the V die in relation to the front of the finger. What is the movement for the R-axis? Sorry, that is incorrect. The up and down movement of the fingers, height, refers to the R-axis movement. If the required flange is 3.5 and the operator actually created a 3.75 flange, what axis must be modified to achieve the required flange? That is not correct. Creating the flange of a part is associated with the X-axis. You have now completed the fourth section of Module 1, Bend Technology, Machine Axes. The next section in the module is Tooling. Welcome to the Tooling section of the Basic Bend Technology module. With an understanding of machine axes and how they affect part creation, we now can turn our attention to tooling. In this section, we'll discuss the different type of punch tooling, how to select the proper lower tool for a program, and how to read the tooling data of a Trumpf tool. After completing this lesson, you should be able to identify the different types of upper tools, read the tooling data of a Trumpf tool, and identify the proper lower tool for a specified material thickness. In the figure, you can see that Trumpf punches come in two configurations, head bearing and shoulder bearing. Punches exist in many geometry and lengths that can be combined to set up multiple tool stations to increase efficiency and reduce operation time. Trumpf tooling is ground on center. This enables the punch tooling to be in a positive position, negative position, or both, which allows for versatility when forming parts. Now let's look at dies. Trumpf dies are available with 4 different angles: 30, 80, 84, or 90-0. Now let's look at dies. Trumpf dies are available with 4 different angles and the choice of which V die depends on the application. A 30-degree V die provide maximum flexibility for air bending angles between 30 and 179 degrees. A 80-degree V die is for air bending of heavy gauge material of any material type. An 84-degree V die is a general-purpose die. It can be used for air bending all material types. A 90-degree V die is intended for bottom bending. Let's review what you've just learned about dies. From the figures below, please select. Yes, that is correct. Bottom bending dies tend to be 90-degree tools. Let's further review what you've just learned about dies. From the figures below, sorry, that is not correct. 30-degree tools have the most flexibility in terms of air bending. Angle ranges can be between 30 to 179 degrees. Let's go further. From the figures below, please select. That's right. Heavy-gauged material can be bent with 84-degree, or general-purpose dies. The tooling configuration and therefore its use in any particular application is defined by the technical data printed on its face. All the data is in metric. Here's a close-up of the technical data printed on the face of each Trumpf punch. The tooling configuration and therefore its use in any particular application is defined by the technical data printed on its face. All the data is in metric. Here's a close-up of the technical data printed on the face of each Trumpf punch. There's one key guideline for selecting the punch: the punch angle should not exceed the die angle. So how do you know which die angle to choose? Here are the rules. For material thickness less than or equal to 1/4 inches, 6 mm, the die angle should be 6 to 8 times the material thickness. For material thickness greater than or equal to 1/4 inches, 6 mm, the die angle should be 8 to 10 times the material thickness. True or false? The die angle should not exceed the punch angle. Sorry, this statement is assume you need to bend a material which is 6 mm thick. Sorry, that's not correct. Here's a summary of the guidelines for selecting a V die opening. If the material to be used is less than or equal to 1/4 inch, 6 mm, using a V die that is less than 6 times the material thickness will result in an increase in the required tonnage, which may exceed the tool rating. The inside radius will be reduced. Therefore die marking is likely to increase as well as microcracking on the outside bend radius. It's important to remember that tooling is always positioned from the left edge of the tool station in relation to the scale on the upper beam. You have now completed the 5th section of Module 1, Bend Technology, Tooling. The next section in the mod, taking into account the bending basics. As a programmer you will need to consider special situations as you are programming to ensure that your operators are working with accurate and effective programs. As you program in Trumpf cinch, you will want to keep in mind situations that will affect your operator on the brake and ensure their safety. Take, for instance, extended flange lengths, as seen in the figure. When bending parts that extend far out toward the operator, be sure to slow the pressing speed to avoid backbending the part or hitting the operator. When programming in Trumpf cinch you will need to realize more than crashes in a program. The bending process has to be considered. A few questions to ask. Are the back gauges in the correct strategy for proper support? Refer to figures. Are the retracts and opening heights decreased in order to reduce production times? And is the finished program as accurate and effective as possible in order for the operator to increase their production output? You have now completed the 6th section of Module 1, Bend Technology, Programming Special Considerations. The next section in the module is ACB, Automatic Controlled Bending. Welcome to the ACB, Automatic Controlled Bending, of the Basic Bend Technology section. With an understanding of the bending basics, we will now discuss a measuring tool that can simplify the bending process. In this section we will cover ACB principles, how to select sensor discs, and the different ACB bend methods. How to activate/deactivate and program ACB tools will be covered later in the training tutorial. After completing this lesson, you should be able to identify the basic ACB principles, identify the correct sensor disc pair for an ACB tool in a bending program, and identify the recommended ACB bend method for use in a bending program. To achieve required parts, precise angles are essential. Material variations, such as spring back and tensile strength, will diminish precision. ACB or automatically controlled bending is an answer to material variations. When using ACB your operator can expect the first part formed using the system to be accurate. There are sensors inside the tool that measure the spring back in material to guide the beam to acquire the required angle. To achieve the precise angle offered by ACB, specific measuring principles are regarded. Two sensor discs with different diameters are used to measure the spring back in material. To do this, the discs are centered to the bend flanges where they make 4 points of contact on the inside bend. ACB calculates the actual angle based on the measured distance between the two discs as they penetrate the die. ACB then recognizes the relaxing point and calculates the needed spring back angle. There are two phases used to achieve an identified measured bend. Identification of spring back in material requires the measuring tool to stop above the lower dead point, LDP. Here ACB takes a measurement in spring back, end of A in figure. The measuring tool releases from the material and calculates the spring back of the material, end of B in figure. The measuring tool penetrates the die to produce the actual angle according to spring back, end of C in figure. And the measuring tool releases a final time to reveal the actual angle of the bend, end of D in figure. Determining the correct sensor discs to use within a measuring tool is essential in procuring precise bend angles. When selecting sensor discs, realize that the usable angle range of ACB is from 45 to 135 degrees. To produce all angles within the range there are two types of discs, R-type for angles between 45 to 105 degrees and L-type for angles between 105 to 135 degrees. Required angle, material type, and material thickness are criteria used to determine the best sensor disc pair to use for creating an ACB part. Please click on Table 1 for a detailed view in a new window. This table is a representation of just a few of the sensor discs available from the Trumpf database. Looking at the table you will find that choosing sensor disc pairs will depend on the angle required, material used, and material thickness. For example, if using the R5, R10 sensor disc pair, Then for materials SS, Al, and ST, mild steel, the maximum material thickness used can be up to 2.5 mm. If using the R5, R10 disc pair for SS, the angle range is from 75 to 95 degrees. So, any program requiring a 90-degree angle, with material less than 2.5 mm, and where the material type is SS, then the R5, R10 disc pair is appropriate for the program. The other consideration to take into account when choosing sensor disk is the type of upper tool used within the program. If you refer to Table 1, you will notice that if deciding to use sensor disks L43, L32, you will only be able to use the pair within an OW203 upper tool. By comparison, the R5, R10 disc pair can be used in any upper tool. Assume you need to produce a trinket box, where you will use SS material at Sorry, that is incorrect. R5, R10, R10, R18, and R9. A major criteria of using ACB is maintaining 4 points of contact between the disc pair and the bend angle. If 4 points of contact cannot be maintained throughout the ACB program, then the properties of the tool cannot be utilized. Once the disc pair has been chosen from Table 1, you will then determine whether or not 4 points of contact can be maintained throughout the ACB program. Table 2 is essential in this determining factor. Please click on the table to the right to get a detailed view. To use Table 2, you will note the program's minimum required flange and the required angle to be produced. Where the two meet on the table will be the minimum flange that can be created with the selected disc pair. Please click on Table 2 to get a detailed view. Referring back to question 1, let's assume we are using the R10, R18 set. Very good. Looking at Table 2, where the 90 degrees in the R10, R18 disc pair meet signifies that the minimum flange that can be created with the disc pair is 18 mm, which is well below the minimum flange required in the program. There are various bend methods available when using ACB. Determining the appropriate bend method for the job will depend on identifying the spring back in the material, grain direction changes, and certain factors within a program, recessed holes, minimized internal flange, or stamped signature, that might interfere with ACB. There are 4 ACB bend methods available. 3 require measuring of material spring back and 1 method does not electronically participate in the bend. They are: identification, measure; regulation or adjust to nominal angle, measure; referencing, measure; and learned, position-based. Identification. Each bend programmed for ACB will require identification of the spring back each time the bend comes up in the sequence. The angle is then adjusted to the programmed value based on the measured spring back. Because a measurement has been made, the angle will be displayed on the brakes controller. Please click on the launch button to view the identification action of ACB on the press brake. Once finished, click the regulation. The spring back data will be identified on the first occurrence only, and then regulated to the required programmed angle form that point on. The following programmed bends are adjusted for the required travel depth based on the measured angle each time the bend comes up in the sequence. Depicted in the figure is a raw sheet with parts laid out in the same grain direction. This is the ideal situation needed in order to properly use regulation. Essentially, regulation is equivalent to a programmed global correction. Every time the identified angle appears in the program, the correction is automatically applied. However, if the blank's grain direction changes, then the angle will be negatively affected. Note: because a measurement has been made, the angle will be displayed on the brakes controller. Referencing. The springback data of a previously performed ACB bend, identification or regulation, is selected and used to adjust the angle of the current bend. Displayed in the figure is a raw sheet with parts laid out to utilize as much of the material as possible. In situations like this, referencing is a proper ACB bend method. During referencing, the measuring tool completes the bend in one try based on a previously made ACB bend, same grain direction and angle. Referencing is useful if you want to save time by eliminating the identification cycle. Measuring tool will not double tap material. Because a measurement was made, the created angle will be displayed on the brakes controller. Learned, based on travel depth beam position at the bottom of the stroke. Copies the beam position, travel depth, from a previously performed identified ACB bend. Learned bending method is unique in that it does not make a measurement, which is an ACB function. Because of this, when the bend is complete, the completed angle is not displayed on the brakes controller. Learned ACB bending is useful if the internal side length of the bend is too small for the sensor to disc to measure accurately, such as what is illustrated in the figure. Learned ACB bending is also useful if the sensor tool cannot directly log a bend angle, for example, sensing in a recess, holes, dimples, or on a stamped signature. When using only one sensor, the angle is measured and the penetration depth is checked and corrected at the position of the sensor. Placement of the sensor should be as close as possible to the center of the tool station. When using two sensors, the angles are measured at the position of the two sensors. If an angle deviation occurs between sensor number 1 and number 2, then ACB makes an adjustment to the parallelism of the beam. When using two sensors for a single bend, the minimum spacing between the two sensors is 600 mm, 2 feet, regardless of the size of the press brake. With bend lengths less than 600 mm, there is no added benefit to using two sensors. When using three sensors, the process is the same as when using two sensors, only a correction to the crowning is applied based on the middle sensor. The only ACB bend method available to use with three sensors is identification. The minimum distance between the outer sensors and the crowning sensor is 500 mm, 20 inches, for a total length of 40 inches. Using an 86-degree V-die with metals that have a large amount of springback. If a sensor bend with an 86-degree die yields a springback angle of more than 3.5 degrees, often the case with stainless steel, an acute angle die of 84 degrees or less should be used to accommodate the springback. If flare-out is the problem, then it is not a question of air bending but bottom bending. In such cases, ACB must not be used because ACB is not designed for bottom bending. Note: inadvertent bottoming as a result of springback can lead to equipment damage or personal injury. Other considerations to keep in mind when using ACB regard grain direction, sheet thickness, and using ACB when bending U-profiles. In the figure displayed are blanks laid out to utilize the most of the raw sheet. In this case, grain direction will need to be considered. Springback angle can differ within the same piece of material due to grain direction. A bend performed with data from a previous ACB bend in the opposite grain direction can be incorrect. To prevent this, switch to identification mode. If possible, reference off another bend in the same grain direction. In sheets thicker than 3 mm, gauging errors can occur when using a 10, 18 mm sensor disc pair. If the smaller sensor disc is already sitting in the radius of the bend, please refer to the figure. This applies especially in the upper measuring range from 105 to 135 degrees. To prevent this, use larger sensor disc pair or the L-series sensor disc, as shown in the figure. When bending U-profiles with the ACB angle sensor, you must ensure that the sensor discs do not collide with the work piece. When the bend is completed, the upper beam will return to the open position. Contact between material and sensor discs are more likely to occur with larger sensor discs such as R18, R19, and R28. To prevent this, reduce the decompression speed so the beam moves up slower, allowing more time to tilt the sheet for removal. Reduce the beam opening height of the Y-axis, which allows the part to be removed by sliding it out the side. And use a smaller disc pair such as the R5, R10, if the sheet thickness and flange length permit. You have now completed this module. When you are ready to continue, return to the main menu and select Module 2, Introduction to True Tops Bend. When bending you have now completed this module. When you are ready to continue, RX1000 controller is used for the demonstration.